Let's start our discussion of real-time scheduling with some basic concepts. First, some terms that we can use to talk about scheduling. The operating system's job is to manage all the resources in the computer system. That includes the CPU, the memory, and I/O devices. A real-time operating system not only provides this management, but also makes sure that operations happen in real time. That is, in wall clock time, not the internal time of the computer. And we often refer to the core of the operating system as the kernel. The terms hard and soft real-time are often used to describe embedded systems, and they're often used in different ways. So let's talk about them. We will use the term hard real-time to mean safety critical. So for instance, the brakes in the car are critical to the operation of the car. If the real-time system that runs the brakes, for example, misses a deadline, that may compromise the safety of the vehicle. Soft real-time we will use to mean not safety critical. So for example, the entertainment system in the car is usually not critical to the safe operation of the car. Some other people use the term hard real-time just to mean stronger deadlines, but we use it to mean safety critical. We use the term program to mean basically what comes out of the compiler, a set of instructions and initial data values. A process is a unique execution of a program. So we can take a program, execute it twice, and we have two different processes. Each process is defined not just by the code, but also by the set of data values. The two processes may have very different data values, even though they're running the same code. A job is a finite time execution of a process. So for instance, if we have a periodic process running, one instance of that periodic process is a job. And then we'll use task to mean a sequence of jobs. We will often use task and process pretty interchangeably, but in more complex systems, we may build a task out of several cooperating processes to do more complex operations. So for example, here is the first job in a sequence of tasks. Here's the second job. Here's the third job. This sequence gives us the task operation. Next, let's talk about how we describe timing for processes. One of the most basic parameters of a program is its execution time or computation time, by which we mean the time it takes for the process to execute without anything else going on in the computer. Of course, with several processes running, the time it takes to finish will take longer. But in order to analyze the real-time properties, we need to know its execution time independent of what else is going on. The release time is the time at which the process becomes ready. So for example, if we're processing data from an audio sample, from a microphone, the sample won't be ready until a certain time. That's the release time for the process. The deadline is simply the time at which the process has to finish its computation. So the process can start at the release time, it needs to finish by the deadline. We can think about several ways in which we want to execute processes. Many processes, such as firing the spark plugs in a car or dealing with these audio samples, are periodic. We have to execute them regularly. But there are also many types of processes we need to handle that don't happen regularly. We refer to these as either aperiodic or sporadic processes. So pressing a button on the dashboard of a car needs to be processed, but we don't need to do that regularly. In both cases, for both periodic and sporadic processes, we can specify release times and deadlines. We'll concentrate, for the most part, on periodic tasks. And for those, we want to think about the period of the processes. That's the interval between process activations. Okay? So here's a set of jobs, and we can identify the period at which those are executed. The initiation interval, or the rate, is simply the reciprocal of the period, or 1 over the period. Now, we can think about what might happen to violate our expectations of timing. We often talk about hard deadlines and soft deadlines. And once again, these terms may be used in different ways by different people. But here we'll use hard deadline to mean that a system fails if the deadline is missed, whereas a soft deadline doesn't cause the system to fail. Okay? Of course, what it means for the system to fail is perhaps up for grabs. But usually we can identify for a particular system what we mean by failure, and so what deadlines are hard and what deadlines are soft. But keep in mind that hard deadlines are not necessarily the same as safety critical. If a printer misses a deadline, it may cause the page to be misprinted, which is clearly a system failure, but it's usually not safety critical. Now we're ready to talk about scheduling and simple ways to evaluate schedulability. A schedule is simply a description of the times at which processes execute. So here is a set of jobs. They execute at particular times. This is one schedule for the system. Here are the same jobs that are executing at different times. So this is a different schedule for the same system. When we evaluate the schedules for a system, we're interested in several things. First, we want to make sure that we can satisfy all the deadlines, that all processes meet their deadlines all the time. We're also interested in CPU utilization, that is the percentage of time devoted to useful work. If, for example, we're not using much of the CPU, perhaps we could use a less expensive CPU. But if the CPU utilization is too high, that may cause it to miss some deadlines. We may also be concerned about scheduling overhead, that is the amount of time it will take for the operating system to determine what should run next. So utilization is a very basic metric we can use to evaluate a system design. The CPU utilization is simply the fraction of the CPU time that is doing useful work. We usually calculate this assuming absolutely no scheduling overhead. So we calculate the utilization over an interval, which we can call here T1 and T2. Utilization is the ratio of the CPU time used for useful work over the length of that time interval, which we can rewrite as 1 over T2 minus T1, which is the length of that time interval, times the sum of the execution time of all the processes. Capital T sub I is the execution time of process I, and we use T2 minus T1 in parens to show that we're interested in the execution time over that particular interval. Sometimes we may abbreviate this simply as capital T over small t. So if the utilization is over 100%, the system clearly won't work. We're trying to use more CPU than is available. If the CPU utilization is 100% or less, the system might work, but it's not guaranteed to work. We can come up with examples in which the utilization is less than 100%, and yet we can't find a schedule that meets all the deadlines. So utilization is a good first check, but it's not the only thing we need to do to make sure that the system is schedulable. Now, how long an interval do we need to determine the utilization, the true utilization of the system, the worst case utilization? Well, that interval is the least common multiple of all the task periods, and that's known as the hyperperiod. So we take all the tasks, we look at all their periods, and we find the least common multiple. Okay? If we look at over the entire hyperperiod, that gives us all the possible combinations of process executions. So the hyperperiod allows us to fully evaluate a schedule. Of course, the length of the hyperperiod depends upon the task schedules, and in some cases they can be very long. So in this example, we have three processes, P1, P2, P3. They have periods of 7, 11, and 15 milliseconds. And the least common multiple of those three periods is 1155 milliseconds. If we change the periods a little bit to 8, 12, and 16, then the least common multiple goes down to 96 milliseconds. That's an order of magnitude reduction. It means it's much easier to check the schedule. Now, can you change the periods anytime you want? No, not in general. The periods are determined by the application designers. Sometimes those periods are very strictly defined and you can't change them at all. But in some cases, the application designers may agree that they could change the periods a little bit in order to simplify the system design. But that decision is ultimately made by the application designers, the control designers, the signal processing designers, and not by the embedded systems programmers. We can use a spreadsheet to evaluate utilization for a set of processes. In this example, we have 3 processes, and for each one we know its execution time and also its period. So in this spreadsheet, we first enter the least common multiple of those periods, which is 5 milliseconds. And then for each process, we enter its period and its CPU time. The last column computes the task execution time, which is the execution time of one iteration of the task, T sub I, times the ceiling of the least common multiple over the period. So that ceiling operation gives us the number of times in the hyperperiod that we'll execute that process. So in the case of P1, its period is 1 millisecond. The least common multiple is 5 milliseconds. So that process will execute 5 times in the hyperperiod. So the total CPU time we need to consider is 5 times the execution of one job, which is 0.1 milliseconds. And that's what gives us the 0.5 milliseconds we see in a spreadsheet. Spreadsheet then adds all those up and then divides by the length of the hyperperiod, and that gives us the utilization. We can use the utilization to judge how effectively we've designed the system, and we can also change the CPU times and the periods to see how that will affect utilization. In summary, we've developed some basic terms such as real-time, hard and soft, processes, tasks. We've talked about scheduling metrics such as deadlines, and we've talked about schedulability, utilization, and the hyperperiod.